whenever you let me.
Yes, please.
I go ahead?
Yeah.
Yep.
Okay, good. So perfect. Oh, I thought you stopped the sharing. Sorry, the recording. Go ahead. Okay, so I start again. Exactly. I'll talk about matrix integrals and the two-sphere partition function. I'll explain every single detail that I highlighted in my elevator pitch. Very good. So to some extent, like what we're going to do in my talk is that we're going to run in a circle. So I'm going to introduce matrix integrals. We'll talk about two-dimensional quantum gravity. We relate two-dimensional quantum gravity to two-sphere. We relate the two-sphere to two-dimensional de Sitter space. And finally, I will try to hint how two-dimensional de Sitter space might be connected to matrix integral. Perfect. So let's get started with a bit of maybe history and more or less review, just to put all on the same footing. So they're like in very, very beautiful work of these four men over here, Berzai, Zuber, and Parisi. They have been studying like a Hermitian matrix integral M. So M over here is an n times n Hermitian matrix. And we're studying the following matrix integral over here, where we're summing over all the n, we're integrating over all the n squared degrees of freedom of this Hermitian matrix. And basically it's the trace over this Hermitian matrix. And alpha 2 is a real valued coupling. And now it turns out that even though seemingly this integral seems to be very, very hard, but essentially because of work of these four men and many other people, they realize that we can use the property that the Hermitian matrix is diagonalizable. So we can reduce this to the real eigenvalues of this Hermitian matrix. And then it turns out in a large n limit, so in the limit where the size of the matrix gets very, very large, we can solve this matrix integral over here. And it turns out that if you introduce this quantity over here, which is basically like the free energy, the log of m, it falls into this expansion over here, into this n squared expansion. So H again is the genus, so it has this genus expansion. And now there's one important remark about this matrix integral over here. So alpha 2 over here, this coupling. A priori, it seems that this matrix integral is only defined if alpha 2 is positive, because if alpha 2 is not positive, then this matrix integral seemingly does not converge. However, essentially because of this large n limit, so if you take the size of the matrix very, very large, if you make this subtle point approximation at leading order, for example, it turns out that all of the eigenvalues of this Hermitian matrix go very close to the extremum of this function over here. And so we can tune alpha 2 to negative values. And this is actually a pretty decent negative value. So for this matrix integral, it's alpha 2 critical is like -1/12. And only if you go further than alpha 2 critical, you have to choose a branch cut. And it turns out that the free energy, for genus H, for alpha 2 close to alpha 2 critical, has this following non-analyticity, where this object over here is called the critical exponent. And now you see it already here, like, I mean, for genus H, this is no longer power law, but it turns out that for genus H, so if you're on a torus, the non-analyticity is no longer of a power law structure, but it is logarithmic. Very good. Now, let me give you some more graphical interpretation of this free energy. So what does this free energy do? So this free energy, it counts diagrams. But it does not count, like, and usually we're used to like Feynman diagrams, for example, where we have like this scalar fields. So we have like single line diagrams. However, because the matrix has two indices, the diagrams of this matrix integral are no longer like single lines, but they're this ribbon diagrams, this thick diagrams. And as has been shown essentially by Berzai, Itzix, and Parisi, and Zuber, for genus 0, we can sum these diagrams in the following way. And then we have these coefficients 2, 18, and so on and so forth. And so basically this 2 over here just means nothing else as there are two diagrams that you can draw on a sphere. We've had a single vertex which emanates 4 edges. And the 18 would just indicate you have like 18 diagrams with 2 edges, and each of these 2 edges emanates 4 vertices. This, for example, would on the other side be a diagram that you draw on a torus. And most importantly, so I mean, in all of this discussion, of course, now we are close to the origin because this is a perturbative expansion. However, it turns out that if you take this sum over here and take the large k limits, so where the vertex number k tends to infinity, you can write this summand over here as k to the power of -7/2. And then you can sum this, you can perform this sum, and it's a polylog, which close to alpha 2 critical exhibits as well as 5/2, which is exactly the critical exponent that we encountered before in the free energy. So these critical exponents are very, very universal for this matrix intervals. Very good. Now, let me also quickly review the two-dimensional quantum gravity side. So because essentially we have this n squared expansion, what we're going to do is that we are assuming that n squared is much, much bigger than alpha minus alpha critical to the power of minus the critical exponent at g0, and this we take much, much bigger than 1. So this is the limit, a specific limit that we are going to take. In particular, this limit is going to guarantee us that higher genera contributions are lower than lower genera contributions. And in this limit, essentially, it has been conjectured that this following identity holds true, so that we can express the free energy of the matrix integral in terms of the gravitational path integral on a genus H surface. And what is this gravitational path integral for me? So, and here we are really following the conjecture of Dissler, David, and Kawai. So we are essentially on a genus H surface, like theta over here is the coupling of this Euler characteristic, the CFT, like this is the CFT that we have been coupling to gravity. This is the ghost action that we introduced because in this action over here, we've been going to Weil gauge. So in 2 dimensions, we can go to Weil gauge. So the ghost action arises because of this gauge fixing. And SL, I'm going to write down below here. But first, let me also comment for a second on this volume of G. So also upon fixing the Weil gauge, there's some residual symmetry left. And basically this G is that residual gauge group. For example, on a 2-sphere, even if you fix Weil gauge, there's still the Möbius transformations left. So G on the sphere would be PSI2C. I will come to this also later. In any case, so upon fixing, going to Weil gauge, so upon writing the metric G in terms of the Weil mode phi, and what is called the fiducial metric G tilde, and this is a parameter B that pops up afterwards in my action, we can write the theory of 2-dimensional quantum gravity in the following way. And this is really due to brilliant and beautiful work of Dissler, David, and Kawai, and many other people. We can write the action in terms of this Liouville action. So where R tilde over here is the Ricci scalar of this fiducial metric G tilde. Lambda is the cosmological constant, which is positive for us still. And Q, and so Q, this parameter Q over here, is related to this B over here in the following way. And most importantly, also Liouville theory is a 2-dimensional CFT. And it has central charge C Liouville, which is connected to this parameter Q in the following way. It's 1 + 6Q squared. And now our matter CFT over here is not an arbitrary CFT, but the matter CFT that we are choosing is a minimal model. So the minimal models, which are basically labeled by these 2 co-prime integers, the 2 co-prime integers for us are the integers 2 and 2m - 1. So for example, there's 2, 3, and or more famously, equally well famous, the M25 model, which is the Yang-Li model. And all of these minimal models in particular, they have negative central charge. So this is basically the series of non-unitary minimal models. And to avoid a conformal anomaly, we need to have this following conservation, like the matter, the central charge of the matter theory, plus the central charge of the Liouville, plus the central charge of the ghosts, which is -26, is equal to 0, which most importantly also relates Q to the central charge of the matter theory. So the parameter Q of the Liouville theory and the central charge of the matter CFT are no longer independent, but they're talking to each other. They're coupled in this following way. Very good. Now, just to give you an example, I've been talking a lot about these critical exponents before. So this conjecture is not falling from heaven. So there's a lot of beautiful work that has been done to establish and to put more evidence towards this conjecture of the duality between matrix models and 2-dimensional quantum gravity. One of them involves what this critical exponents essentially. So for example, we have like for M23, which is the minimal model that has only the identity operator and vanishing central charge. If you're in genus H equal to 0, so if you're in a sphere, then it has been shown by that the gravitational path integral on the sphere, it's of the following form. So basically, if we perform the shift phi, like phi is going to phi minus the logarithm of lambda over 2b, then it has been shown by Dissler, David, and Kawai, and Knisnik, Polyakov, and Samologikov, that the gravitational path integral takes the following form. So there's a lambda to the power of 5 over 2 in particular. And we remind, like in the matrix integral, we also found this non-analyticity, this same critical exponent is 5 over 2. So this was one of the first evidences towards towards this conjecture. And basically, it implies that the quartic matrix integral, this matrix integral for Gaussian and the quartic interaction, is dual to two-dimensional quantum gravity coupled to this minimal model M23. And this is basically very, very beautifully also encoded in this picture, where these black lines, these are basically this ribbon diagrams of the matrix integral, and the magenta lines on top of it. This is like the dual lattice, because two-dimensional quantum gravity sums over Riemann surfaces. So this is this dual lattice. Very good. Now, I've been talking about this rather simple, still very beautiful matrix integral, like the quartic matrix integral. We can also generalize this matrix integral. So we can just say, okay, let's not stop at an m to the power 4 term, but let's add other even powers of m. And this is essentially what Kazakov did. So when he introduced the multi-critical matrix integrals, and this really generalized the quartic matrix integral. So the mth multi-critical matrix integral is defined in the following way. So we're really just like be adding other even powers of m, and then instead of like having a single coupling alpha 2, now we have alpha 2, alpha 3 to alpha m, and all of this like are real value couplings. And much in the spirit of this quartic matrix integral, where we had a single critical point, in the multi-critical matrix integral with a multi-critical point. So all of these couplings can assume like critical values. And if you tune all of these couplings to this multi-critical point, take n to infinity, it has been conjectured that the mth multi-critical matrix integral is dual to two-dimensional quantum gravity, coupled to essentially exactly this minimum models m to m minus 1. So, and just to already make a small comment here, in this matrix integral over here, we have m minus 1 couplings. We have alpha 2 to alpha m. And the minimal model, like essentially like this minimal model over here, there's m minus 1 primaries. So the number of primaries in the minimal model agrees with the number of couplings that we have in the matrix integral. So this will guide our way now. Perfect. But before actually it will guide our way, I wanted to just show you this following thing, because I think it's very, very beautiful. So also, like, of course, this multi-critical matrix integral is also generalized, like the diagrammatic of the quartic matrix integral. So if you're going close to the origin in coupling space, where the couplings are very small, we can perform a perturbative expansion. And defining like this free energy, like equal, like as minus the log of the matrix integral. Also, F counts connected diagrams, but it generalizes the quartic matrix integral, because in the quartic case, we only had like these numbers 2 and 18 over here. So this really like counted the diagrams, the connected diagrams where each vertex was emanating 4 edges. And now that we have also this order 6 term in the matrices, we can also count diagrams whose vertices emanate like 6 edges, which is essentially this 5, 300, and so on and so forth. This is all by like the genus 0 really meaning here that I'm on a sphere. So these are diagrams that I can draw on a sphere. And like, for example, 144, this is the number of diagrams that I'm with like 2 vertices, and each of these vertex emanates like 4 or 6 edges. And of course, like it's possible to generalize this to arbitrary m. So they're very beautiful combinatorial techniques. And just for fun, maybe, like this is basically for general M. We obtained this expression over here, and then you can really like extract whatever number of diagrams that you're interested in. So I will not even try to spell out this number because I only have an hour. But this number would count the number of connected diagrams with 9 distinct vertices emanating 4 to 20 edges. Perfect. Now, as I was promising like 2 or 3 minutes ago, though, let me go to explain you the relation between the m-1 primaries of the minimal model and the m-1 couplings of the multi-critical matrix integral. So basically, I'm focusing for the time being on m = 3, which is, and the continuum side is like the Yang-Lee model. So in the m = 3 model, I have two couplings. And what I can do now is that I can be like, so here's the multi-critical point, and I can basically build a path that goes from the origin coupling space to the multi-critical point. But it's pretty obvious right from the get-go that I can choose, I mean, there's not a single path. There are multiple different paths that will lead me from the origin to the multi-critical point. And in particular, there are like these 2 paths that I will call the identity path, as will become clear in a second, and the minimal path. So these are these 2 different paths, but they approach the multi-critical point in very different ways. So t is between 0 and 1, so it really connects the origin to the multi-critical point. And then it turns out that if you write the free energy F in terms along the identity path, close to the multi-critical point, it will behave as 1 minus t to the power of 7/2, so the critical exponent is 7/2, whereas along the minimal path, the critical exponent is 7/3. So these are remarkably completely different critical exponents. And this is what I like explained in this picture. And now on the next slide, it will become clear why I've been calling them the identity path and the minimal path. So the m = 3 model, like this matrix integral, like we just remind you again, like it was this matrix integral m squared plus alpha 2 m to the power of 4 plus alpha 3/6 m to the power of 6. So this matrix integral is conjectured to be dual to 2-dimensional quantum gravity coupled to the Yang-Lee model. So the Yang-Lee model has like these 2 Virasoro primaries. So what can we do is that we study like Liouville theory coupled to this minimal model, and then we turn on one operator of the minimal model. So that's what I'm doing over here. So, and because as I was pointing out before, because we are in the 2-sphere, and we fix the Weyl gauge, which though still implies that we have the Möbius transformations which are still there. But then we basically have the Liouville action, the CFT, the ghosts, and then we turn on one of the operators of the minimal model. And here's sigma r over here is chosen in such a way that this combined operator over here is a marginal operator. So it has conformal dimension 1, 1, which in particular implies that if you integrate it here, it has 0 conformal dimension. And now, as I was pointing out before, it turns out that the m-1 primaries of the minimal model, so if you turn on one of these primaries, one of the m-1 primaries of the minimal model over here, then these primaries exactly correspond to one of the m-1 distinct paths in the m multi-critical matrix integral. And to explain you again, like along this Yang-Lee model, which has like the central charge -22/5, and 2 Virasoro primaries, so it has the identity operator with conformal dimension 0. So basically there's O11 with conformal dimension 0. And then there's a minimal operator, which has conformal dimension -1/5. Following the ideas of Dirichlet, De Wit, and Kawai again, the gravitational path integral on the 2-sphere, its scale is the following way. So it's either the 7/2 or it's the 7/3. So in the same spirit as for the quadratic matrix integral, we have this match of the critical exponents between the matrix integral and the gravitational path integral. And from that, so this way, I hope I gave you some more evidence to, that helps us understand this conjecture. But one of those things that I will focus in the later part of my talk are also going to be these coefficients over here. So I have these coefficients both in the matrix integral, well, had these coefficients in the matrix integral and also in the continuum picture. So these are genus-dependent coefficients that we will focus on in the following part of my talk. Very good. Oops. Yes. Now, okay, I'm coming back to the gravitational path integral. So on the previous slide, we've only considered like the sphere, but this is really possible in general dimensions. So we have this highly fluctuating path integral in 2 dimensions. This is really the major obstacle of like 2-dimensional quantum gravity. It's highly, highly fluctuating a priori. And where now following this Liouville and Kawai, what we've shown on the previous slide, like just for the sphere, you can really generalize this. So where if you still perform this same shift that you shift the Weyl mode phi in the following way, then the log of this gravitational path integral for arbitrary genus H, you can always find it in the following way. So, and for example, like in here, this coefficient over here, if you would plug like the kh equal to 2, so if you would be on a sphere, and then you take the central charge, for example, this minus 22/5, you're going to recover the 7/2. Why the 7/2? Because in principle here, like by turning on, by just considering that this lambda times e to the power of 2b phi, implicitly we're turning on the identity operator of the minimum model. So that's why we find the 7/2 and not the 7/3. Perfect. And there is this promised FH of CM, which we're going to encounter in some of the following slides. Because for example, like if you're on the sphere, then this coefficient over here will get contributions from the gauge fixing of PSL2C. And furthermore, it will also get contributions from some Feynman diagrams, as we will see. Perfect. But before I can go to the Feynman diagrams and the gauge fixing, let me remind you again that in general, the gravitational path integral is very strongly fluctuating. Summing, as I was pointing out in the elevator pitch, we have all geometries, and then for the given genus, and then we're summing over all the genera. So, however, if you take C matter squared to infinity, which gives you 2 possibilities, it gives you the possibility to take very large negative central charge or very large positive central charge. And now say you're on this sphere, so you're on genus H equal to 0. And then you impose this area constraint. So you're not taking an arbitrary sphere, but you're taking a sphere which has area 4 pi upsilon. Then the gravitational path integral admits around S2 subtle. So as I was pointing out before, we started with a topology, but now we have a geometry. And this is very, very important because this a priori does not happen for 2-dimensional quantum gravity. We don't have a saddle. Only in this specific limit. C matter going to minus infinity, and we fix the area of the underlying surface. The other point B, which is maybe something a little less familiar, like C. I was telling you before that we have to avoid the conformal anomaly. We need to have the constraint C matter plus C Liouville plus C ghost, which is minus 26 here, equal to 0. But if C matter is going to be very, very big, C Liouville has to be very, very small. And a Liouville theory which has a very, very small central charge, that's basically Timelike Liouville theory. So in Timelike Liouville theory, we switch the sign of the kinetic term. However, it turns out that Timelike Liouville theory, or the genus 0, admits a real sphere saddle. So also Timelike Liouville has this sphere saddle, as has been observed by Polchinski and in very beautiful work also by Wittenhall and Miles from 10 years ago. And also in a paper that we are going to study, we've been studying this Timelike Liouville theory saddle in a paper that's also going to appear tomorrow or like this week. Perfect. But now, wait, I will focus for the time being on case A. I have some slides in the end, which would also discuss case B. And the reason being that I'm focusing on case A is because I've been talking so much about the matrix integral. So the big point there, like the big positive thing about point A is that we have a round 2 sphere saddle. We have a Euclidean DS2 saddle. But case A also has a matrix picture. So we also have a microscopic picture for case A. So that's why I'm going to focus on case A for now. Very good. So we have case A, we have a very large negative central charge, and we are in this 2 sphere. and we are going to fix the area of this two sphere. So we choose the Fubini's 2D metric for the two sphere. So we have this metric over here, which is, again, it's the Weil factor, and then this fiducial metric over here. And the fiducial metric, as I was saying before, is this Fubini's 2D metric. And now what we're studying is we're studying the fixed area partition function of genus 0. So we have the gravitational path integral of genus 0, and then we impose this constraint over here. So we are imposing that the area of the two sphere that we're taking into consideration is fixed to have area 4 pi epsilon. And then it turns out that we can write this fixed area partition function the following way. Let me explain this a second. So well, I'll come to A at last, maybe. So PSL2C are basically the Möbius transformations, the residual gauge group upon fixing the Weil gauge. A priori, the PSL2C is infinite, so I'll explain in a second because we have to do a Fadeev-Popov gauge fixing for the PSL2C. E to the power of 2 theta is because we are the sphere, so we have other characteristic too. Symmetry over 6 and minus 26 over 6. This is well following the claims by Samologikov and other people with like telling us what's the behavior of a CFT on a sphere of area epsilon. This e to the power of minus 4 pi lambda epsilon, that's what we pulled out using this area constraint from the Liouville action. The epsilon to the power of minus 1, we also pulled out from the delta function over here, because if you write the physical metric over here in terms of the Weil mode and the fiducial metric, then the metric of the fiducial metric is going to have an epsilon, and if you pull it out of the delta function, it gives you an epsilon to the power of minus 1. And now, then additionally, we've been introducing a Lagrange multiplier alpha, and this Lagrange multiplier fixes basically our area. So this does nothing else than imposing this constraint over here, where the omega is the volume element on the two sphere. And now that's the point. So if you have this area constraint, if we have a very large negative central charge, we can tame all the fluctuations. And the equations of motion of phi basically tell you that there's phi star equal to 0 is a saddle. Along alpha star equal to this expression over here. But if phi star is equal to 0, the physical metric is equal to the fiducial metric. And we have the geometry of a two sphere. Perfect. Now, what are we going to do? So now, basically, we have found this two sphere. Now we're adding fluctuations to this sphere saddle. So we're going to add like a delta phi and a delta alpha to the two fields that we have in the theory. So phi star is the saddle, which was 0 here, and like basically this combination for alpha star. And we're adding small fluctuations, delta alpha and delta phi. In the limit where b is going to 0, and let me just maybe remind you that I mean, we have like q is equal to c major minus 25 over 6, and b plus b inverse is equal to q. So, sorry, I've been writing it down for Timelike level. So it's 25 minus c major. So when c major is going to minus infinity, q is going to be very, very big, which using this relation implies that b is very, very small. So that's why all of these limits, c major going to minus infinity, implies q very large, implies b very small. So I will use this limit interchangingly. So in a semi-classical limit where b is going to 0, the fixed area partition function has the following form. Essentially, exactly these are these factors from the CFTs on the two sphere. This is this factor that we pull out from the area constraint. And then we have this perturbative piece over here. This perturbative piece really encodes these fluctuations on the two sphere. And it takes the following form over here. So it's an action in terms of delta phi and delta alpha. And this, the minus Laplacian, is the Laplacian of the fiducial metric. And basically, this is like the mass of delta phi. And here we have like higher order fluctuations, higher order powers in delta phi. So there's delta phi to the power of 3, then there would be delta phi to the power of 4, and so on and so forth. And then there's importantly, there's also like delta phi and delta alpha are talking to each other. So the fluctuations of these two fields, phi and alpha, they talk to each other. And what we can do now is that we are in a sphere. So a basis a complete basis on the sphere or the spherical harmonics. So we can expand delta phi in terms of the spherical harmonics. And this then obey the following eigenvalue equation. So like the eigenvalues of the spherical Laplacian are basically the following quantities over here. Like the upsilon here is appearing as essentially because, I mean, this is the Laplacian on G tilde, and so it also has an upsilon, so just to match all the dimensions. And now what becomes very, very clear here is the L equal to 1 modes, they're very subtle. So because if you basically put this eigenvalue constraint in here for the L equal to 1 modes, this is basically an almost zero mode. So the L equal to 1 modes are very, very subtle. And this L, in particular, this almost zero mode is only lifted at order B squared, but B squared is very small. So it really seems that we have an almost zero mode in our theory, which is very, very subtle. However, something is going to help us. And this something that's going to help us is this following object over here. From the get-go, we have been modding out the volume of PSL2C. We've been modding out the volume of the Möbius transformations, which are still there, even in 2 dimensions, even if you go to Weyl gauge. And so in one way or another, we need to fix the volume of PSL2C because otherwise we're dividing by infinity. Now, what are we going to do? So it essentially turns out that the Liouville action itself is invariant under PSL2C. And this is very important because first of all, this also tells us that we're not just dividing by PSL2C, but we have upstairs and downstairs the volume of PSL2C. And so basically the whole thing essentially makes sense. And basically the transformation that the Liouville action is invariant under is the following expression over here. So Q was just this parameter in the Liouville action, and F here is an element in PSL2C. F is a Möbius transformation, so like F is just AZ minus B over CZ minus D with like AD minus BC equal to 1 and AB and C and D in complex numbers. And so basically PSL2C has 6 real degrees of freedom. So what we can do, like one possibility to fix the volume of PSL2C is to choose that the 3 L equal to 1 modes are 0. So we choose the constraint delta phi 1m for m between -1 and 1 is equal to 0. This way, basically, we remove 3 degrees of freedom of PSL2C, and we are left only with 3. What we are left with is the maximal complex subgroup of PSL2C. We are left with the SO3. And if we do then the Fadeev-Popov gauge fixing, using essentially really like this constraint over here, what we find is the following quantity over here. So this object over here is like a 3J symbol. And in particular, of course, the Fadeev-Popov determinant is manifest invariant under SO3 and the SO3 asymmetries. So, and this phi is, I mean, so maybe I remind you, like, I mean, we've been expanding delta phi in this basis of spherical harmonics. So these are just these coefficients over here. And what's very clear also here, so there's a Q and there's a Q to the power of 3. So the Fadeev-Popov determinant has important effects basically now, if you put it in the path interval. And this is also what we're going to see here. So now as promised as well, if we want to understand this path integral in the semi-classical limit, in the limit at fixed area and in the semi-classical limit where we take B to 0, equivalently C matter going to -infinity. We have this perturbative action, we have this perturbative piece in the path interval. And now what we do is we impose this gauge fixing constraint. So we add this delta Fadeev-Popov. And we add this constraint that we put this 3 L equal to 1 modes to 0. And putting this 3 L equal to 1 mode to 0 essentially lifts the fact that we had almost 0 modes. It was exactly the L equal to 1 modes that were our almost 0 modes. So they're gone. Now, to some extent, we're in business again. Because now this action over here does not have any almost 0 modes anymore, because the L equal to 1 modes, they have just been set to 0. And maybe as a side remark, like this measure over here is really just a flat measure on the field's delta phi. And now we have this action over here. So we have quadratic pieces over here, and then we have this interaction term between delta alpha and delta phi. So to basically get rid of this interaction term, delta alpha, delta phi, we can diagonalize the action. And then you get like basically a quadratic term in delta alpha and a quadratic term for the phi equal to 0 mode, because the only mode that delta alpha is talking to over here, because of the orthogonality of the spherical harmonics, is the L equal to 0 mode. And that's why I've been writing down this 4 distinct, more or less, propagators over here. So we have the propagator of delta alpha, we have the propagator for the L equal to 0 mode, which talks to the Lagrange multiplier. I've been also stripping off the L equal to 2 modes, because as we've seen in the previous slide, the Fadeev-Popov determinant is a function of the L equal to 2 modes. So the L equal to 2 modes are going to be affected by the Fadeev-Popov determinant. And then we have all the modes with L bigger or equal to 2. And of course, I mean, I don't have a propagator for the L equal to 1 modes because they're gone because of this constraint over here. And what we're going to end up with then is that we have to study Feynman diagrams on the 2-sphere. And some of the diagrams that we are going to encounter are the following kind of diagrams. So there are these double tadpoles and melons and some cactus diagrams and many others. Very good. So what we are going to end up with, at least up toward the 2-loop, so if you study all 2-loop contributions on the 2-sphere, is the following quantity. So we are only modding out by the volume of SO3. We are in the 2-sphere, so there's e to the power of 2 theta. And then these are all the upsilon contributions. So I think this is just very beautiful. So I'm going to explain this a second, where these different contributions are coming from. So the orange contributions here, they're coming from the fact that we have this contribution from the CFT on the sphere. Equivalently, this minus 26/6 was again the contribution from the ghosts. Then we have this minus 10/3 plus b squared, which comes because, of course, at the Gaussian level, we have to do a functional, we have to calculate the functional determinant, because otherwise we have an infinite product. We have all the L modes. And so doing a heat kernel analysis, we find this additional upsilon dependency over here. Whereas this -1 over here, it came from the delta constraint. And then, of course, this 9/2 is because we've been treating the L equal to 0 modes, the L equal to 1 modes, and the L equal to 2 modes separately. And the degeneracy at each L is 2L plus 1. So this is basically a half, 3/2 plus 5/2. And then lambda UV is a UV cutoff. And then additionally, what we have is the following perturbative expansion over here. So for B being going to 0. And importantly in here is 1/b to the power of 4. This is very important because this 1/b to the power of 4, what did it get contributions from? It got contributions from the measure. So sorry, from the Fadeev-Popov gauge fixing. So the Fadeev-Popov gauge fixing basically contributes very, very heavily to this semi-classical expansion of the fixed area partition function at genome 0. And then subsequent, we have like 1/b squared, order 1, b squared, and so on and so forth. And the other very, very important piece that's popping up over here is this additional contribution from the Fadeev-Popov gauge fixing. So the Fadeev-Popov gauge fixing, the contributions from there heavily contribute with this perturbative expansion. And very good. I think I got all my contributions. Very good. Now, let me connect this to some very, very other beautiful results in literature. So given
sure. When you send the semi-classical B equal to 0, you're fixing the UV cutoff scale, lambda UV, I guess?
Yeah.
I see. Then the whole quantity is going to be very small because there is a exponential suppression.
Sorry, which is very small?
The lambda UV to the power.
Yeah, lambda UV goes as 1/L squared, so 1/L UV squared.
I see. And then there is a power of that, which is the which goes to -infinity. So the whole
exactly. It basically kills the dimension in upsilon.
I see. I see. I see. Okay, thank you.
You're welcome. Thank you so much. It's a very, very good question. I mean, I've been really keeping lambda UV explicitly because it's on my next slide. You're also going to see why it's very important that we kept lambda UV explicitly. So lambda UV is been dropped a lot in the literature. So and for us, it was really important to keep it also because there's an important comparison also to make with the DOCC formula. So because essentially Liouville theories is CFT, the structure constants for the 3-point function, they're known in very, very beautiful work by Donardo, Samologikov, and Teschner, and many other brilliant people, which turns out that this 3-point function can be written in the following form. And these coefficients over here are these DRCC coefficients. And then following like these ideas of Samologikov and Donardo and Teschner, we can also calculate the partition function on the sphere by integrating the DRCC formula 3 times with respect to the cosmological constant. And if you expand the partition function that you get from the DRCC coefficient in small b, we're getting the following expansion over here. And very, very importantly, like to some extent, what we've been doing is that we've been taking this contribution that we get from DRCC into different pieces. So what is the meaning of each piece in this expansion, basically? We've seen that 1 over b to the power 4 got its contributions, for example, from the Fadeev-Popov gauge fixing. And that also in here, in this contribution, the Fadeev-Popov gauge fixing does give contributions. Other pieces in here come really from diagrams from the 2-sphere. And so that's also why it's very important to keep lambda UV, because the expansions, they do agree with each other, but this is very scheme dependent. So lambda UV, for example, we introduced it in order to do this heat kernel analysis for the functional determinant. But in order for these two quantities to match, so ours comes really from a path integral analysis. The DRCC formula came when you consider like Liouville theory on the disk. So for example, in the DRCC formula, the UV cutoff has been set to 1, presumably. That's why we don't see it in this expansion over here. So for us, like it's also like very beautiful to just like see how these two expansions, like what's the scheme dependency? How can we really match these two expansions, like the coefficients of these two expansions, I mean, because the structure agrees. Very good. Now, let me just give you again the dictionary. So I've been starting with telling you, okay, there's this conjecture duality between matrix integrals and 2-dimensional quantum gravity. And I've been showing you these critical exponents over here. And these are really the critical exponents for the identity operator. So we had this identity path in the matrix integral that was leading to the multi-critical point with a specific critical exponent over here. So this was the 7/2 or the 5/2 for Yang-Lee or M32 model. And in the continuum picture, we had this lambda to the power of m plus 1/2. So these were really just matching with each other. Now, okay, the critical exponents have been studied well, but we have this subtle. So how do we get more evidence in favor of all of this? More evidence in favor of all of this conjecture, and in particular, like possibly getting a realization of the 2-sphere in the matrix integral. So possibly getting an understanding of where's the sphere in the matrices. What we have to do is to also understand these coefficients over here, like this coefficient and this coefficient, basically. Now, of course, what you're going to tell me now is that if I'm studying a single genus, this is highly ambiguous. So I can always do some shifts, and then I can always absorb everything, and my single genus coefficients, they're highly ambiguous. And that's basically why we're not considering a single genus, but what we're doing is that we're considering ratios. So we're studying the theories, the matrix integral and the continuum theory on different genera. And unfortunately, genus 1 is always a bit special. As we've seen already in the matrix picture, we have this logarithmic non-analyticity. So instead of studying genus 1, instead of studying the single torus, what we're doing is that we're studying the double torus. So what we are taking is like the free energy at genus 0, the free energy at genus 2. For example, this combination over here, this is really a function of M. And maybe I should give you maybe I should have done this before. So the parameter B in the Liouville theory is related to M in the matrix integral in the following way. So in particular, this really means that if B is going to 0 in this semi-classical limit where we had this expansion of the gravitational path integral, that basically means that M, the power of this matrix polynomial tends to infinity. So we have a very large, basically have this infinite product. And so basically, if we then want to calculate the free energy of the matrix integral on a genus 0 surface and then a genus 2 surface, we can, on genus 0, we can do the saddle point. On higher genus, we have to use other techniques, for example, like orthogonal polynomials or the string equation. And what one finds is that the free energy on genus 0 is the falling object, and then on genus 2, it's this object over here. And then what one can do now is that we can study the ratios of F0 and F2. So this is basically what we are doing in the matrix integral. And on the continuum perspective, here we have to study Liouville theory also, and as well as CFTs, but gauge CFTs. So our CFTs are coupled to gravity on higher genus Riemann surfaces. And fortunately for us, the Liouville side has been studied by brilliant people in the MAF community. And also for the CFT point of view, we can try to get some generalizations of the Verlinde formula for some gauge CFTs on higher genus Riemann surfaces. The punchline really is that in order to find evidence of the sphere in the matrix model, what we're doing is that we are comparing ratios. Very good. And now let me kind of conclude, or let me get to the last part of my talk. So the two-sphere and two-dimensional de Sitter space. So we are living in an asymptotically de Sitter universe. So understanding the de Sitter entropy is pretty crucial, pretty important for ourselves. So okay, we are living in a four-dimensional space-time. So by 2 dimensions, de Sitter in 2 dimensions resembles in very, very many important details 4-dimensional de Sitter space. So that's why we're also, for the time being, restricting to 2D. If we don't understand 2D, how should we understand 4D, basically? So we have this 2-dimensional Euclidean de Sitter space, and 2-dimensional Euclidean de Sitter space is the two-sphere. So that's why I've been also pointing out already in my elevator pitch. Finding this geometry, this saddle in 2-dimensional quantum gravity is very important to understand, because it could help us understand de Sitter space. So Euclidean 2-dimensional de Sitter space is this metric, the metric of a sphere. So theta is from minus pi over 2 to pi over 2, and phi is this angular coordinate that goes from 0 to 2 pi. And then what one can do is, and one can perform Wick rotations. And from the sphere, there are actually 2 possibilities. So we can Wick rotate to get to the global patch, which is this full diamond over here, or we can Wick rotate to get to the static patch, which is just this diamond over here. So we can basically, from the sphere, from Euclidean de Sitter, reach both the global and the static patch of de Sitter space. Now, what's important about the entropy of the de Sitter space? So first of all, we have still no idea what's the entropy of the de Sitter space. Like, what does it count? What's the microscopic origin of the de Sitter entropy? It's of order 10 to the 120, and we don't know what it means. But there are beautiful conjunctions. So basically, in a de Sitter universe, because of this accelerated expansion, an observer in a de Sitter space-time is surrounded by a cosmological horizon. This is very much maybe in the spirit of a black hole horizon. Just that for the black hole, the horizon is appearing because of this accumulation of matter. For the de Sitter, it's basically because everything is moving away from us. And Gibbons and Hawking, what they've done is that they have associated an entropy to this. They told us that the entropy for the de Sitter spacetime is encoded in a Euclidean path integral. So a Euclidean path integral. Throughout my talk, we've been studying Euclidean path integrals. So basically, our goal, our hope is that we can understand some pieces of the de Sitter entropy, that we can calculate the de Sitter entropy semi-classically. And by connecting it to the matrix integral, which has, even though like the microscopic origin of the de Sitter entropy is completely unknown, the matrix picture, the matrix integrals, this has a huge, beautiful history, and there are like many techniques that we can just like use. That the matrix picture might actually help us to understand some pieces of the microscopic origin of the de Sitter entropy. And we always in the Euclidean signature. So maybe we would like to get to the Lorentzian picture as well. So then there's the question, what's the Lorentzian picture of the fixed area constraint? And maybe, like, I mean, we had before, like we had this area constraint that I've been imposing using this Lagrange multiplier. But basically, there's another term in the Liouville action, which also has this term e to the power of 4 pi. Well, maybe I don't need it. E to the power of e squared x g tilde e to the power of 2b phi lambda. So this comes from the Liouville action, and this comes from the area constraint. So possible approaches to get a Lorentzian picture is that we can just include this alpha into lambda, basically get a complexified cosmological constant. And then much maybe also in the spirit, like, okay, going back to Coleman or in more recent literature, and actually very pretty also, like I think Ida in like one of my next talk is going to talk about this averaging. So maybe much in this spirit, what we have to do is that we have to average over a complexified cosmological constant to understand the fixed area perspective in the Lorentzian picture. And well, I put one other slide that just gives more hints towards this entropic picture. So what we've seen is that really like this fixed area path integral at genus 0, it had this form over here. And we're really putting a lot of emphasis into this F0 symmetry over here. But other pieces that are in this formula that might actually ring a bell is really like this symmetry over 6 with this upsilon over here. This is nothing else than the 2D CFT entanglement entropy, which has been like going back to work of Wilczek, Larsen, Calabrese, Cardi, Myers. So this is really like this first piece. This is just a CFT piece. And now we have subleading corrections over here. So these subleading corrections, they might really stem from the fact that we couple our CFT to gravity. So this coupling the CFT to gravity might really also help us understanding what are the effects of uncoupling a CFT to gravity. And now on the other side, what are the coefficients of the log in the matrix picture? So it's basically the growth of these Riemann surfaces. So we had in the matrix picture, we had all these beautiful diagrams over here, like, I don't know, like something like that. But okay, maybe speculative and whatever, but the de Sitter entropy counts something. The matrix integral counts diagrams. So maybe there is even some connection between like counting diagrams and a de Sitter entropy. And very good. So I think I'm basically on time, so I will not get into Timelike level, even though I would have it here, but maybe for later sometime. I think that's it. So we are for the two-sphere, and I think penguins are amazing creatures. So thank you very much.
Thank you so much. Okay, so now time for questions or comments from the audience.
I think it was very physicsy, so I hope I didn't lose anyone.
Any questions?
Maybe I did.
Why don't you ask a question? Yes.
So let me ask a very elementary question to summarize whatever. So on the gravity side, the parameters are theta, lambda, and after you fix the minimum model, then you don't have any other parameters. Is that right?
Yes.
So on the side of the matrix integral, there are multiple parameters in the action of the matrices, but yes, they're supposed to be determined by fixing the dictionary.
Exactly. Yes, exactly. That's a brilliant question. I mean, that's a really brilliant question. So exactly. Wait, I had one help. I just do it here. So as you were pointing out, we have like theta and lambda in the continuum side, and what theta does correspond to in the matrix. So this is continuum, and then we have the matrix. So in the matrix, theta is basically log n, and this is very good because, for example, here you have 2 theta. So in the matrix picture, because theta is log n, this is basically n squared. This is a discrete parameter. And as you're pointing out, so this is the discrete parameter in this theory. we also have this continuous parameter, lambda, the cosmological constant. And in the matrix perspective, lambda corresponds to alpha minus alpha critical. And because alpha minus alpha critical is positive, this gives like, this basically is compatible with the fact that we're studying like spacetimes with positive cosmological constants. I hope this answers your question.
So in the action in the early part of your slide, you had the coefficient alpha 2, alpha maybe 3, alpha 4 stuff.
Yes,
so the alpha critical has to be a function of those parameters, and the alpha critical is supposed to be related to the lambda, right?
Yeah, exactly. So alpha. So I mean, for example, for the quartic matrix integral, like alpha 2 critical was like -1/12. For this is the M23 model, and then we had the fact that the free energy was close to alpha 2 critical, was growing as alpha 2 minus alpha 2 critical to this specific power, which, for example, on genus 0, it has been 5/2. And it was merely matching to the fact that in the gravitational path integral on genus 0, we had found that it went as lambda to the power of 5/2. So this is how these two parameters get identified with each other.
So alpha 2 is something like capital lambda plus alpha 2 comma c.
Exactly.
All right. That's an example of dictionary.
Exactly.
Thank you.
You're welcome. Thank you so much for the very good question.
Okay, other questions? So I have one question. So there was a comment about this Lorentzian. If you go to Lorentzian signature, there's a cosmology. You might want to sum over different values of cosmological constant. Could you explain that a little bit more?
Oh, I would hope, I would love to, I would seriously love to, but this is very speculative yet. So the Lorentzian interpretation of all of this. So, I mean, we're still struggling with this a lot because it's really not obvious how to get the fixed area constraint from a Euclidean signature to a Lorentzian signature. So this complexifying the cosmological constant and averaging is one possible thing, but much more there is, unfortunately, not.
Maybe not all the details are fleshed out, but what is the relation between analytic continuation versus the average?
Oh, I'm just meaning that, I mean, basically we could basically like write like lambda tilde as like lambda plus I alpha, and or taking other functions of lambda.
I see. I see.
That's it's a very innocent comment in principle, so, but it's yeah.
I see. Okay, thank you.
You're very welcome. Thank you for the question.
Okay, so we have time for questions or.
Oops.
Yeah, so there is still time. So maybe you can talk about the. I mean, if you can explain the case B in 5 minutes or so.
Oh,
I do that.
Of course, that's why I have more slides. So also because I think it is very beautiful. So, and so of course we also have like this case B, which was a Timelike level. And for us, the important thing here was also that we could contrast and compare like case A to case B. So essentially, as I was pointing out, case B is nothing else than a Timelike level. So here, this sign of the kinetic term is going to be switched. So that's why this theory is called Timelike level. And to go basically from space-like level to Timelike level, what one is doing is that we send B in space-like level to plus minus I beta, and capital Q to minus plus, just the other way around, minus plus IQ. And then you go from space-like to time-like level. And then basically also rotating phi. So phi is then going to minus plus I phi. To have this also like a 2 beta phi. And then basically we're finding this time-like level action. And on the sphere, the gravitational path integral still mods out the volume of PSL2C. So we also still have to do this gauge fixing. But now here we have the time-like level action. And it turns out that if you calculate the equations of motion of this theory, it does allow for the subtle phi star equal to 0. So basically, if also in here we've been studying the metric, which is ds squared equal to e to the power of 2 beta phi. times the ds tilde squared, which also here we can take the Fubini-Studi metric. If phi star is equal to 0, then ds squared is equal to ds Fubini-Studi squared. And so we also find this real semi-classical saddle. In maybe, and importantly for case B, we didn't have to fix any area. So in principle, this Timelike level would be much easier to be analytically continued to Lorentzian signature. However, the problem with the Timelike level theory is that there is no matrix interval description of Timelike level theory known. So space-like level theory is conjectured to have this matrix interval description as well. Timelike level theory doesn't have that. So that's what's the drawback of Timelike level theory at this stage, basically. However, this is essentially my setup. So here I'm really just comparing, but these are crucially different. Like the expansions in small b or small beta accompanied in case A by this fixed area, and this C-matter going to minus infinity, or in Timelike by C-matter going to plus infinity. The expansion is very, very, very different. So and so here we had, this 1 over b to the power of 4, and here it goes as 1 over beta. And here we only had these odd terms, whereas here we have even terms. And the contribution of this 1 over beta over here is also coming from the Fadeev-Popov. It has basically, it's a 1 over beta to the power of 3 from the Fadeev-Popov. But then the saddle here will give us another beta squared. That's what's this going to make this a 1 over beta. And maybe even equally important, what's very different between space-like and Timelike is this plus minus I over here. And where's this plus minus I coming from? So the plus minus I in Timelike is really coming from the fact that in Timelike lower theory, basically because we have this negative kinetic term, there all of these modes are Gaussian unsuppressed. So basically, if we also like expand this phis around the saddle in small fluctuations, all of the modes are going to be Gaussian unsuppressed. Now, we can biquotate them to like upwards or downwards, all of the modes. This way, we will get an overall I, which is a local term that we can absorb in the measure. However, it turns out that the L equal to 0 modes, it's still Gaussian unsuppressed. And so the L equal to 0 modes, we have to biquotate. And that's what's giving us this plus minus I in Timelike level theory. In space-like level theory, on the other side, we have two Gaussian unsuppressed modes. So in space-like level theory, both the L equal to 0 mode and the delta alpha, like the Lagrange multiplier fluctuation, are Gaussian unsuppressed. And because we have to biquotate two fields, they kill the I. They mutually kill the I, basically. And that's why we don't get any I in space-like level theory. And okay, I didn't put this on my slide, but one of the very beautiful results that we also obtained is that I've been talking about the DOCC formula before. The DOCC formula is a result that holds true for space-like level theory. Now, there are several conjectures also of the structure constant, the 3-point function structure constant for Timelike level theory. And following just the logic of space-like level theory, where we got like taking these three derivatives with respect to the cosmological constant of the sphere partition function, which is equal to minus C B B B. We got a result for the sphere partition function here, also for Timelike level theory, which allows very, very nicely for analytic continuation. So the structure constants seemingly, therefore, must also allow for an analytic continuation. And basically, that's what we've been showing in the paper that's going to appear this week, for example, is that there's really an analytic continuation of C beta beta beta, which maybe a little compared to what some claims also in the literature, it's not equal to 0. So in the literature, the claims are showing that C beta 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 possibly is equal to 0. If we're just like doing this analytic continuation with the gravity partition function genus 0, it's non-zero. So, and it basically matches, almost matches. I will not get into the details. There's this 3-point function, this analytically continuous 3-point function of 3 area operators. And I think now I should really stop because otherwise, yes,
yeah,
I could continue forever, but there's still no matrix picture for Timelike level theory, which is a pity.
I think there's another question.
Yeah.
Sorry?
Yeah.
Hi, can I ask a question?
Yes.
Yeah, I'm a little confused about the role of de Sitter space. So, I mean, the role. I mean, what is the mean? Where is the de Sitter space fitting? So I understand that two-dimensional de Sitter space is S2, but
Yeah.
this S2 is some. I mean, it's the string world sheet that is S2, right? It's not the target space that is S2 that you're talking about. Target space is some other complicated theory. Is that correct?
I think so, yes. But I'm not super, yes. Oops.
No, so I got confused by these comments about de Sitter and even possibilities of calculating de Sitter entropy and things like this. Yeah, over there. So the matrix, what is the relation of the matrix integral to de Sitter space?
So basically, I think this is best maybe explained hopefully in this slide over here. So if we just follow basically the ideas of Gibbons and Hawking to some extent, and these 2 theta over here, basically it could be interpreted as the tree level, de Sitter entropy, horizon entropy. And given that the theta in, as I was asked before, like theta is identified with log n in the matrix picture, the tree level entropy seemingly in this identification would be n squared. And an entropy is a discrete quantity, and n squared is a very discrete quantity as well. So, I mean, these are high goals and high hopes as well. But so we have this n squared over here. And then we have this corrections over here, this with like log epsilon in the matrix as well, in the matrix as well. And then we have this quantity over here in the matrix picture. So all of these quantities here, indeed, like as I was saying here, this over here we can maybe interpret as this subleading as these effects upon coupling the CFT to gravity. But there's also a quantity in the matrix associated to them. So it might give like ideas of what's possibly counted. And it's really like the hints or the like something very beautiful is really that this is already the tree level is in the matrix picture is something very discrete.
Maybe ask it in a different way. Suppose you could calculate not just the tree level, but all genera.
Yeah.
Right. So in principle, suppose you had the power to do that and you add it up. Does that have an interpretation in de Sitter space?
I don't know.
Okay. Meaning as some quantum corrected object, or is it just that it happens to be the case that one of the diagrams, has the topology and maybe geometry of de Sitter?
Yes. No. Yes. Yeah. That's for sure. Yeah.
It's the latter. That's clear. But the question is there also
for the higher genera? You mean?
Yeah. I mean, is there a physical interpretation in the matrix model? Is it is any observable of de Sitter an observable of the matrix model? Maybe that's the right way to ask the question.
Well, I mean, not at this stage. I mean, all of this relation between matrix integrals and de Sitter, this is really like a very modern, like a very, at the moment, like for us, like kind of trying to identify the 2 quantities with each other. I think I mean, all of this is very speculative. I think that the point that the only thing that I can really say at the moment is this genus 0, these 2 theta and the n squared.
Okay,
and then of course the lambda with the alpha minus alpha critical.
Thank you.
Welcome.
Okay, I guess it's time. So let's thank Beatrix again.